speaker for the event in Gammage from Dutch, I suppose, and the title is Mirror Symmetry and K-theoretic Coulomb branches.
Thanks. Yeah, so thanks for inviting me. Big honor to speak here at the occasion honoring Kenji Fukaya, who, I'm a huge fan of your categories. I hope to compute a few of them in this talk. So this is based on some joint work with Ben Webster and Michael McBreen. The paper's not up yet, hopefully will be in the next week or so. So just to situate ourselves, let me just sort of remind everybody that in representation theory, a major goal, which is called the geometric Langlands program, is to understand homological mirror symmetry for Hitchin systems. So these are holomorphic symplectic or hyperkähler manifolds. Hyperkähler, which have the structure of an integrable system. So this is an integrable system. So the generic fibers of this map are holomorphic Lagrangian tori. So, right, so that's what people care about. So recently, there's been a new construction by Braverman, Finkelberg, Nakajima of a new machine that produces lots and lots of examples of spaces of this form. So this is the, lots of examples come from the so-called K-theoretic Coulomb branch construction. Of Braverman, Finkelberg, Nakajima. So I'm not going to go into details of what this construction is, but let me say that whatever it is, this thing is a multiplicative or loop group analog. It produces by the way, all these three words, multiplicative, loop group, and K-theoretic, all kind of mean the same thing to me in this context. It produces some sort of multiplicative analog of many familiar hyperkähler spaces. So for instance, the toric hyperkähler varieties, also called hypertoric varieties, the Springer resolution, which is the cotangent bundle of the flag variety, or even more general than hypertoric varieties, is Nakajima quiver varieties. So these are like some classes of spaces that we really care about in representation theory. And so this four-dimensional Coulomb branch construction gives some sort of multiplicative versions of these spaces, which I'll say more about in a minute. But today's talk is going to be about this first one today. Because these hypertoric varieties are the sort of simplest possible example of these kinds of spaces. And so today I'm going to prove a sort of mirror symmetry equivalence explaining homological mirror symmetry for these hypertoric varieties. And I'm going to try and explain it fully in a way that makes clear that the structures at play are structures not just that you see in this simple case, but that you see sort of in general in this family of things, which is why I'm situating them in this sort of 4D Coulomb branch world. But if you don't like that, then you can forget all about that and just consider that, like, for the rest of this talk, I'm going to define some varieties and compute some things about them. So what is a multiplicative hypertoric variety? So first of all, I should tell you what a traditional additive hypertoric variety is. So first of all, let me tell you what a toric variety is. So I know everybody in the room already knows what a toric variety is, but I'm going to say it anyway. So a toric variety, so from now on, I'm going to fix a torus inside of C star to the n which I'm going to call T, and I'll write G for the quotient of C star to the n by T. And so now, what's a toric variety? It's, I start with C to the n, and then I do a Hamiltonian reduction by T, or by the compact real torus inside of T, which I'll denote by TR. I may not always be careful about whether I'm dealing with complex or compact tori, but you can ask me if there's confusion. Right, so this is a toric variety. It's this kind of Hamiltonian reduction. And alpha is, of course, inside the dual of the real dual of the Lie algebra of this torus. It's a moment map parameter. So now, what's a hypertoric variety? Hypertoric. This is going to be almost exactly the same construction, except instead of C to the n, which has a Hamiltonian action by this torus, I'm going to start with the cotangent bundle to C to the n. So this is a hyperkähler space, and it has a hyperhamiltonian action by this torus. So, and I take a hyperkähler reduction by this torus. So now I have two parameters. Alpha is what it was before, and beta is inside the dual, the complexified dual Lie algebra now. And what beta is that, just to remind you, in case you're not familiar with the hyperkähler reduction story, is that beta is a moment map parameter for the holomorphic symplectic form, which on T star C to the n is, of course, sum of dxi wedge dy. So what this construction is here, let me give this guy a name. Let me call this variety x alpha beta. So x alpha beta is equal to, I take a moment map preimage of beta with this complex moment map for this holomorphic symplectic form, and then I do a Hamiltonian reduction of that with Hamiltonian reduction parameter alpha. Of course, there's various more symmetric ways to write this, but this is a perfectly good way to write it down. Okay, so that's what a hypertoric variety is. I'll give you examples in just a second. Let me just say what a multiplicative hypertoric variety is. Let me just say what a multiplicative hypertoric variety is. So the focus of this talk is the multiplicative hypertoric varieties. And this is going to be very similar to the construction I just had, except instead of T star C to the n, I'm going to start with n copies, not of T star C, but of T star C minus a conic. So I start with n copies of this T star C minus xy equals 1. And now beta is going to be not in the dual Lie algebra, but actually in the dual Lie group. Because the action of this torus T is quasi-Hamiltonian for this complex symplectic form, which is now dx wedge dy over xy minus 1. So that means it has a group valued moment map. But otherwise, the definition is the same thing. I take the preimage of beta under this group valued moment map, and then I take a Hamiltonian reduction by alpha. Okay, so that's the definition of these spaces. So now let me say some examples. So hypertoric varieties. So if I take T to be I don't know where to stand here. If I take T to be the diagonal, the one-dimensional diagonal torus inside of C star to the n, then this construction is going to produce me the cotangent bundle of P to the n minus 1. Which makes sense, right? Because like if I did this construction for a toric variety, I would get P to the n, and here I'm getting the cotangent bundle of P to the n. And similarly, if I take T to be the sort of anti-diagonal torus, that is to say the kernel of the multiplication map from C star to the end to C star, then I get a resolution of an ADE singularity. So, okay, so those are some examples of hypertoric varieties. And I should say that, so later on, I'm going to say that this data of the torus T and also these parameters alpha and beta, I can summarize in terms of hyperplane arrangement. So I'm not going to say yet where that hyperplane arrangement came from, but I'm just going to draw those pictures here. So, for T star P to the, for T star P1, I get hyperplane arrangement that looks like it's going to be a one-dimensional hyperplane arrangement. So I'm going to have a real line, and I'm going to have two hyperplanes here and here. For T star P2, my hyperplane arrangement is going to be in two-dimensional space, and I'm going to have three lines that look like this, this, and this. So I haven't told you where these hyperplane arrangements come from yet, but you should already see a pattern that this thing looks a lot like the moment polytope for this, this space that I'm doing here. Or I guess what I've drawn is what Alan Knudsen would call the moment X-ray, that I'm seeing the moment polytopes for all toric fixed points here. So like in this picture, you should see that this is a P2. And now, you know that these correspond to the toric strata of P2. These are the three divisors, and these are the three fixed points. But now I've drawn also their conormals. So this like open area here, you should think of as being the conormal to the line at infinity inside P2. Or this area here, you should think of as being the conormal to the origin, or the point 0, 0 inside of 0, 0, 1, whatever, inside of P2. So this is just these hyperplane arrangements, whatever I've drawn, they look like some fancy way to summarize the combinatorics of some toric varieties that appear inside of T star P2. I'll make this precise in a minute when I talk about the multiplicative hypertoric varieties. So maybe I should go there now. Right, so the simplest, multiplicative hypertoric varieties. So the simplest multiplicative hypertoric variety is, of course, the case when when n equals 1 and t is trivial. So in that case, you just get this space itself, which I know many people in the room are experts in, but I will review anyway. So what is this space, C2 minus xy equals to 1? Well, one thing we know about it is it's got a, there's a lot of things you can say. I could spend a whole talk talking about it. But one thing we can say is that, this S1 action that we have on it gives you this hyper-Hamiltonian moment map that we've seen, which has a real part and a complex part. So this guy has a map down to R times C star. Or equivalently, by fiddling around with the parts of this thing, I can treat this as a map to R2 times S1. And so that gives me a projection down to R2. And so if I think about what this projection looks like, it's going to turn out that the generic fiber of this projection is one of these holomorphic Lagrangian tori I mentioned at the beginning of my talk. And the special fiber is the only singular torus in this integrable system, which has a nodal singularity. Cool. It turns out that this space, okay, so we're going to be interested in mirror symmetry for these multiplicative hypertoric varieties. Like, this looks like a good setup to do mirror symmetry. It's like something with a torus vibration. So, all right, we're stoked. So it turns out, I think the earliest state, well, you can see a good exposition of this in Denis' paper on mirror symmetry and the complement of an anti-canonical divisor. Although, of course, this space has many incarnations going back a long time. This space is self-mirror. So this space is self-mirror. one way to interpret that statement, if you think about mirror symmetry as dualizing all of the tori in this vibration, is that somehow each of these tori gets dualized, and then this single singular torus gets dualized to another singular torus. So in some sense, this statement is about telling you that the nodal curve is self-dual, which is a very interesting statement in algebraic geometry, of course. Right, so we'd like to understand some kind of mirror symmetry statements for the general multiplicative hypertoric varieties. And so what it's going to turn out is that yeah, so maybe I'll say this. So proposition I name these hypertoric varieties, these multiplicative hypertoric varieties. Oh, I didn't give them a name. I called the other one X, so let me call this one Y. Y alpha beta. So the statement that I'm going to be interested in is that Y alpha 1, so when beta is 1, that's like that's the trivial moment map parameter. That this thing is mirror to y0 exponential of alpha. So there's a lot of different ways to understand this statement. There's a very careful description of SYZ mirror symmetry for additive hypertoric varieties, which ends up touching these multiplicative hypertoric varieties in a paper of Suchong Lao and Zhao Zheng. And you can also understand this statement by using some of the tools developed in the Abuzai-Aru-Katsargov paper on mirror symmetry for hypersurfaces. This will be a sort of one of these complete intersections of conic bundles, if you sort of think about what imposing this moment map parameter is doing. But let me just say another way to think about this, which is Hori-Vafa mirror symmetry, which is that if I have a space X, or a space Y in this case, with the action of a torus T on it, that should correspond to, so a Hamiltonian action of a torus T on Y should correspond to, well, I should say you can find this sort of statement made in Telemon's, Konstantin Telemon's ICM address. If a Hamiltonian torus action on Y should correspond to a map from the mirror of Y to the dual torus. And then taking a Hamiltonian reduction of this map, so if I take a Hamiltonian reduction of Y by T, this should be mirror to taking the fiber, if I call this map F, taking the fiber of X alpha. So this is basically the procedure that Hori and Vafa used to produce their mirrors to toric varieties, and sort of the same thing works in this case. So maybe one other thing to say, and sort of maybe the more interesting statement than just the kind of one statement I've made here, is that a more refined statement, say that? A more refined statement is that this space y0, 1, where I take both of these parameters to be 0, which is singular, so the singular space y0, 1, this thing is self-mirror. And the mirror map which is going to identify the complex structures and the Kähler structures on the two mirror pair, which are the same thing here, sends the Kähler deformation parameter alpha, which, if you remember, was a Hamiltonian reduction parameter. So it's, if I'm thinking about this in complex geometry, it's a GIT parameter, and it's controlling the resolution of this singularity. So when I take alpha to 0, I'm collapsing the divisors I got when I resolved this thing. So that Kähler parameter gets sent to the complex structure parameter. Beta equals x to alpha. So beta was a group valued moment map value. So I told you the definition of this was that you impose an equation, something is equal to beta, and then you take your Hamiltonian reduction. So it turns out that moving beta away from 1 will smooth this. It's a deformation of this complex thing that will smooth it. Yeah. I should mention that this singular thing is also affine. So if I just turn on beta and don't turn on a resolution parameter, then I'm going to get something that's still affine. So this is sort of the setup here. And there's, of course, a lot of very interesting questions you can ask about what happens to these categories as you sort of deform these parameters in various ways, and what kinds of deformations do you get. In the talk today, I'm going to be focused about mirror symmetry at one fixed point in this moduli space, which is the one I wrote there. Maybe I'll write the statement to the main theorem, and then hopefully someone will start asking questions at some point. So I've defined for you some class of spaces that we're interested in. I've told you from SYZ mirror symmetry, however you like to do it. You can figure out that what things are mirror to each other, and so you should want to try to prove that. So theorem with McBreen and Webster is that the Fukaya category of this affine variety, y0 beta, x alpha, is equivalent to the category of coherent sheaves on the resolved thing, y alpha 1. So okay, and I should make a comment that this is at the level of derived categories. Maybe I'll write DB code just so that there's no confusion. It's going to turn out that there is a natural T structure on this thing, and there is an abelian category underlying it, but it's not going to be the abelian category of coherent sheaves. And I'll say a couple of words about that closer to the end of my talk. But this is the statement of the theorem. So are there any questions so far? Yeah.
So what do you mean by Fukaya category in this case?
Right, so yeah, good. So I'm about to say that, but I'm going to use the work of Ganatra, Pardon, and Shenda, who have told us that we can use these Lagrangian skeleta to compute Fukaya categories. So I'll go into more details of that there, but I am using that work. And I'm using it maybe in slightly more generality than it's actually been proved. I think technically I'm using this co-sheaf property, which, as John mentioned, is still in progress, but it may be possible to avoid that, I'm not sure. Probably. Any other questions? All right. Right, so okay, so as I just mentioned to Yanki, we learned from, well, again, we've learned from several talks already, especially Maxime's first talk this week, that a good way to study Fukaya categories is by studying their Lagrangian skeleta. So study Fukaya categories. Of course, if your symplectic manifold is compact, you can't do that, or you have to do some very difficult procedure that Maxime described to us. But if your Fukaya category is of an affine manifold, which is, say, Stein or Weinstein, study Fukaya categories of Weinstein manifolds by studying their Lagrangian skeleta. So one of the main sort of points of this talk is going to be that if you have a variety of this form, which isn't just affine, but it's actually holomorphic symplectic, I mean it's hyperkähler, then you might be able to hope to have a skeleton, a Lagrangian skeleton, that's actually a holomorphic Lagrangian. And it turns out that is a huge help in calculating the category. So that does turn out to be what happens here. So where does this Lagrangian skeleton come from? Oh, I haven't given examples of these multiplicative hypertoric varieties yet. Well, I guess I sort of have. Let me just say that, oh good, I still have it up here so I can make an example. It's easy to say what the example is corresponding to this thing here. So one example of multiplicative hypertoric varieties, if I take T again to be this kernel torus, then I will get a multiplicative version of this resolution of ADE singularity, which is going to be C2 minus this locus xy equals 1 mod C mod A. So you can see that this thing I deleted avoids the singularity, which happens at the origin. So that's kind of a general phenomenon here, is that like I'm deleting something, but it's away from whatever singularity I had. So sort of these things look a lot like affine, the additive hypertoric varieties. And I'm about to explain the difference right now.
Sorry, you said ADE, but you write only C.
Oh, sorry, did I say ADE? I didn't mean to say ADE. Yeah, so the type D and E is also interesting. I mean, you know more about that than I do. Yeah, just the type, because hypertoric varieties are only the abelian quiver varieties, so you only get the type A singularities here. Right, so, okay, so nobody has any other questions? Everybody's really happy? Okay. So I'm looking at this multiplicative hypertoric variety y alpha beta. I got it by doing a Hamiltonian reduction by this torus T. But I started with an action of this full torus C star to the n, which I just erased. So I still have a residual G action. So G acts on y alpha beta. And so I have a moment map down to the G version of what I had before. Oh no, I shouldn't have erased it. This was where all the good stuff was on this board. Oh well. So I have a moment map down to, so before, over here, I had a moment map down to R times C star, R2 times S1, which was like, you know, this was the version when I just had an S1 action. If I have a G action, then I'm going to get a map down to GC times check times GR check. That's the dual torus, the complex dual torus to G times the real dual Lie algebra. Or as over there, I can split it in a different way, and I can get GR check times GC check. Both of these are interesting, so I really should have said something about the other projections, so maybe I'll do that in a second. But let me just say that once again, I can project this thing down using this projection down to GC check. And let me call this composite map F. And now the theorem is going to be that F is the fiber over 0 is a Lagrangian skeleton this is a Lagrangian skeleton. In fact, it's better than that. As I mentioned, it's a holomorphic Lagrangian skeleton. Of the variety y. Right. So okay, in order to have a Lagrangian skeleton, I needed to be affine, so I better have taken alpha to be 0. Right. And now this is a holomorphic Lagrangian skeleton of y0 beta.
What do you mean by is a Lagrangian skeleton?
Well, it's a Lagrangian.
Yes.
And there exists a Liouville structure such that this is the stable set for that Liouville structure. Right, so yeah, so let me explain where this came from. So first of all, you know, okay, so in this case, it's obvious, but I'm going to go through it anyway because it's a good example. Right, because I wanted to say something about the other projection here. So this T star C minus xy equals 1 down to, so I saw that this had a projection down to R2, but it also had a projection down to C star. And this C star projection is just, this is the xy minus 1 plane. So if I draw this picture, I've got my generic fiber is going to be a copy of C star, and my special fiber is this guy. And now, you know, how do I produce the Lagrangian skeleton here? Well, I have a usual trick. If I have a Lefschetz vibration and I want to understand a Liouville field on it, you know, then, or I want to understand like a symplectic form or whatever on a Lefschetz vibration, I should like sort of try and combine things happening on the base and things happening on the fiber. And so it turns out that sort of getting something, sort of getting the precise structure you want on the fiber is like very difficult. But since I'm sort of only caring about things up to, I just want like a Liouville form that does approximately what I want, then it's not so difficult. And I can combine these in order to get a flow that is maybe like my flow on the fiber might have some sort of horizontal part, but by making sure I have a very big flow horizontally coming from this guy, I can make sure that I'm doing whatever I need to here, and I'm doing what I need to on the fiber. So, right, if you start with a Lefschetz vibration, you're usually in a good setup for producing scalata. And now you can sort of repeat this trick in the general case here. So once again, I have this map down to GC check. And I have sort of, that's going to give me the horizontal part of my Liouville flow, which is going to give me this sort of, in the base here, it's going to look like this compact torus inside of GC. And then in the fiber, I'm going to have something that a generic fiber of this guy as before is like a copy of C star. Yeah, and taking the quotient by T doesn't mess up the positivity of the form or anything. So, okay. So I've given you a map and told you that the zero set of that map is a Lagrangian skeleton, but I haven't told you what that Lagrangian looks like. Oh good, I've kept my hyperplane arrangement here, so happy. All right, I'm going to erase this picture in that case, which we've all memorized. So now I'm going to tell you how to draw this hyperplane arrangement, which, as we saw, captured a lot of the geometry of these additive hypertoric varieties. Maybe we didn't see it, but we could guess it. So what we're going to do is we have a map from the dual C star to the n, C star to the n, dual, whatever, down to T check, which I'll call P. And then I'm going to define G check beta to be the preimage of beta under this map. In fact, I'm going to do everything with real tori here. So this is now an S1 to the n, S1 to the n, whatever. So now the coordinate tori inside of here, so this thing is a copy of G because this was an exact sequence of tori, and it lives inside of S1 to the n. So I can try intersecting this with the coordinate tori, and those give a hyperplane arrangement inside of this torus, G, this real torus, G check beta. So okay, so you might ask, what's a hyperplane arrangement inside of a torus? And all I mean is that if I have a map from the dual Lie algebra of G to here, and if I pulled back along this map, this exponential map, then I would sort of unwrap this hyperplane arrangement I have here to a periodic hyperplane arrangement in here. So you can just think of hyperplane arrangement in torus as being the same thing as a periodic hyperplane arrangement. And the relation between that and the hyperplane arrangement I've already defined for you is going to involve passing to the universal cover of my multiplicative hypertoric variety along this covering map from Lie algebra G to group G. Check. Let me not worry about that now. Let me give examples. maybe I go, God, I don't want to erase that. I don't want to erase that. So, an example. So, if I have, you know, T is the diagonal torus again, then what do I have? I have exactly these hyperplane arrangements I had before, except now they're inside of a torus. So for n equals 2, I like just take this line and wrap it up to a circle, and then I get my 2 dots here. And for n equals 3, I put this guy in a torus. Maybe I should use a different color. Right. So this is my hyperplane arrangement inside of a torus. And maybe it's easier to see what's going on if I move this horizontal guy so he's sort of flat here, and move this vertical guy so he's here. So now, you can see that this hyperplane arrangement divides my 2 torus into 3 different chambers. 2 of them are triangles, and 1 of them is a hexagon. So now the theorem, proposition, whatever, is that F inverse of 0, or this Lagrangian skeleton L, is a union of smooth, well, orbifold, whatever, smooth orbifold mean the same thing to me. Orbifold toric varieties. And not only that, but they're described by these polytopes, whose moment polytopes are chambers as above. So this guy is going to have a skeleton that is made out of 2 copies of P1, or 2 S2s, that are kissing at 2 points. And this guy is going to have a P2, another P2, and then P2 blown up at 3 points, and then they're glued together in this way. That, like, the line at infinity in this P2 looks like this divisor in this guy, and so on and so forth. So that's very cool. Just to give you a little example here, well, maybe, I don't know, maybe it's sort of already clear from the example that I just erased that sort of the standard space of C2 minus xy equals 1 just had sort of a hyperplane arrangement, the circle with a single dot in it, and that was the sort of nodal curve there. So, right. So now we're able to compute the Fukaya category. So I'm good, I still have this written here. We should study Fukaya categories by looking at their Lagrangian skeleton. So near this xi, the Fukaya category looks like a category of constructible sheaves on xi with some singular support conditions, and you can see that the singular support conditions are exactly the conormals to toric strata, because like that's where the skeleton, like if I zoom in on this P2, or oops, this is added, whatever, same thing. If I zoom in on this P2, then from the perspective of the P2, the skeleton is just the conormals to toric strata inside the P2. So locally near any one of these toric varieties, the Fukaya category looks like sheaves on the toric variety with micro support in the conormals to toric strata. So that's nice. That's a category we can compute. And the way we can compute it is that, so I mentioned before that this is a holomorphic Lagrangian. Here's where that comes into play. This guy has a natural T structure whose heart, which generates the category, is the category of perverse sheaves. So perverse sheaves on xi, again with singularities along toric strata. So the point is, so first of all, I should say that from work of maybe Jin, and probably other people, but maybe just her, I don't know, in like a Nadler-Zaslow type equivalence between Fukaya category and constructible sheaves, the perverse sheaves are supposed to correspond to holomorphic Lagrangians. So in this case, we have enough holomorphic Lagrangians to generate the whole Fukaya category, and these guys have much more rigid behavior. As was hinted at, for instance, by work of, I guess, Solomon and Verbitsky from last year. So there's a lot of ways to see that, if you have holomorphic Lagrangians, then they're sort of very rigid, and it should be a lot easier to deal with their Floer theory. This is sort of maybe the sheaf-theoretic manifestation of that I have this category of perverse sheaves. And so it turns out this category is easy to compute. So how do I compute it? Well, let me just give you an example sort of computation to help you get the flavor of it. So let me suppose x is equal to c. It's the simplest toric variety besides c star. So I'm looking at sheaves on C with micro support in the conormal to this toric stratum. So if I sort of view this picture microlocally, I'm seeing this conormal up here. And then the whole point of the category of perverse sheaves is sort of, all you need to know is, well, I know all you need to know, but well, whatever, it turns out that this category has a famous description. It's a category of two vector spaces, which you might call the nearby cycles and the vanishing cycles, and that there's, well, these guys have monodromies from going around these various C stars, and then there's two maps between them. So let me write this a different way. This category, so perverse sheaves on C with a possible singularity at 0 is equivalent to the data of a pair of vector spaces, V and W, a pair of maps, X and Y, with the requirement that 1 minus XY is equal to M1, 1 minus YX is equal to M2, where M1 and M2 are the monodromies on these guys. So you could eliminate M1 and M2 and just declare that 1 minus XY and 1 minus YX have to be invertible. So it's a perfectly simple way of computing this thing, if you know your way around perverse sheaves. And so now I can see how to define my category in general. So what I'm going to do is define a quiver with relations. So I'm going to have vertices are going to be chambers in the hyperplane arrangement I drew before, right? Because I should have, like, from the perspective of this P2, my perverse sheaf wants to know what its microstock is on the P2. And from the perspective of this P2 and this guy, BWU, it also wants to know what its microstock is here. But then from the perspective of this P2, this guy is like a conormal coming off the P2, which we already saw should have like two maps going back and forth. So pairs of edges at each facet of this hyperplane arrangements. So from this V, you get a pair of edges going back and forth, you get a pair of edges here, pair of edges here. I've already drawn these guys, these here, these here, these here, these here. And then relations. The relation is the same relation as this guy here. So you see all the relations already in this one picture, that if I go back and forth, then that's the same thing as doing a monodromy around that toric divisor. So if I go do one edge and then back along that edge, that's the same thing as monodromy around that toric divisor. So now I've given you a category, I've given you like a quiver with relations, and now, theorem, the Fukaya category of this Y0 beta is equal to modules over this quiver with relations. And so you can see that this category actually has a natural T structure, which is just like, because nothing was derived about this thing that well, everything is derived, but nothing has to be derived about this description I gave you. So yeah, I can treat this as an abelian category of modules. And so objects of that abelian category should be holomorphic Lagrangian branes inside the Fukaya category. And this category has some natural projective objects, which is just, it's a quiver representation. So it has one projective object at each vertex. And these are precisely the, I forget what John called them, but These are the cocores that generate the linking disks that generate the Fukaya category. So very cool. Any questions about that? Okay. So I've given a presentation of this category, and now I see I've maybe gone too slowly, so I didn't have enough time to say lots of things about the B side, but I'll say some things about it. So the goal of this talk, I should say, is, well, two goals. One is like, oh, perverse sheaves are good for computation. The second goal is to explain where this hyperplane arrangement appears on the B side. So I want to study coherent sheaves now on Y alpha 1, which is a resolution of this singular thing, Y01. Maybe I just erase the coherent sheaves for now. So I have this kind of resolution of singularities, and it turns out that there's a very nice way to produce tilting bundles on symplectic resolutions developed by Roma Vezirkovnikov and Dima Kalyedin, and probably many other people have done work on similar aspects. And so to understand this category of coherent sheaves, maybe I'll say it this way, to understand coherent sheaves on this guy, Y alpha 1, use the quantization and characteristic P trick. Quantization in characteristic P. So I don't have time to go into detail on this. If you've never seen it before, I can tell you the broad strokes, which is that the idea is that, let me do the additive case first, how you would compute coherent sheaves on the additive hypertoric variety, which turns out to be very similar. So the idea is that if you start with AN, you notice that if I look at functions, so let F be characteristic P, the field of characteristic P. Now functions on T star AN is given by, right, like x1 dot 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 xn, c1 dot 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 xcn. You can sort of quantize this, deform this, by passing to the ring of differential operators on AN, which is equal to something generated by the xi and also by the del I, which don't commute with them. And then the trick in characteristic P is that this thing has a big center. So that's the whole idea, is that this has a big center. And so the center of this guy is equal to just the pth powers of these guys. Xi to the p, del I to the p. If I had a more complicated thing than AN when I started with, then I would take the pth powers of all my functions and the pth power of my differentials minus the restricted power. But anyway, in this case it's this. This embeds into D. But now I can note that this thing turns out to be the same thing as functions on the Frobenius twist of the thing I started with. So that's, again, some more characteristic P magic. But the moral of this story is that this sheaf of differential operators defines an Azumaya algebra on this Frobenius twist. If you remember, an Azumaya algebra is just some algebra that locally looks like a matrix algebra. So the idea here is that this thing is going to look like a sort of non-commutative resolution of this singular space Y01. Which maybe someone should have been skeptical before when I told you that these things were mirror, because I told you, oh, I erased it. But in the statement I told you, I was matching up a complex parameter beta with a real parameter alpha, right? So in order to really match those up, I needed sort of alpha to be a complex parameter. So it turns out alpha is there's not only a direction controlling the resolution, but there's a direction the sort of imaginary direction, where y alpha 1 is sort of telling you to take modules over this Azumaya algebra, which is derived equivalent to the category of coherent sheaves on y alpha 1. So sorry, that was a lot of words, but the point is that, oh yeah, so, sorry. You can do a quantum Hamiltonian reduction of this thing now. So I take D, which, as before, was functions on the x's and del's. Then I impose the moment map, which is now kind of a quantum moment map. Maybe I impose it with a parameter alpha, and then I do the quotient by t, which is passing the t invariance here. And this thing is going to give you an Azumaya algebra on this Hamiltonian reduction of T star A for Frobenius twist. Okay, so that's that was a very sketchy, fast heuristic construction, but the point is I have some way of producing an Azumaya algebra on this guy. And maybe I'll just make a remark that, this is my hyperplane arrangement, maybe I'll just make a remark that to do this for the multiplicative guys, the multiplicative hypertoric varieties replace your sheaf of differential operators that you used to deform here. You're going to need an even further deformation by the Q difference operators, which is x del, except now the non-commutativity is del x minus q squared. X del is equal to q squared minus 1. This was done in some work of Yordan Ganev and Nicholas Cooney, working out this story for the multiplicative hypertoric varieties. Okay, so suppose I do this thing, I get something which it's possible, I get some algebra. At the end of the day, you can black box everything I said, and you can say that I have some algebra now, which I'll just call A alpha. This is going to be an algebra, and it's going to be derived equivalent to the category of coherent sheaves on a resolution, although it came from this sort of Azumaya algebra from quantization and characteristic P. And now I can ask, okay, how do I understand the category of modules over this algebra? And I note that I did a quantum Hamiltonian reduction at some point by T, but as before, I have a residual G action. So I can ask for the G weight spaces of this algebra. So everything now is graded, all the modules over this algebra, maybe I should say. G acts on this category. And so if I look at the G equivariant objects, I can take weight spaces. So I have, I get some projective objects, which I'll call P lambda, for lambda a character of my torus G, with the property that Hom from P lambda to another module M will pick out the lambda weight space inside of M. So these, so these P lambdas are a bunch of projectives. I get one for every co-weight of G. And now I don't want to erase this board because I'm about to say something about the hyperplanes. So I can erase this. So okay, I produced you an infinite number of projectives, which is too many projectives because I want like a finite type description of this algebra. So I can ask, question, when are two P lambda isomorphic? So okay, let me draw the co-weight lattice of G. Whatever, it's a bunch of dots, which you can't even see because they're in blue, sorry. And then it's going to turn out that I can draw some walls, and that these P lambdas are non-isomorphic exactly when you cross one of the walls. And okay, well, I'm not doing a good job of drawing them, but spoiler alert, it's going to be exactly the same as the walls in the hyperplane arrangement we saw before. So I think that's pretty incredible. Right, so they're non-isomorphic exactly across walls, and then it turns out that, so theorem, this category of coherent sheaves on Y alpha 0 is also equivalent to modules over this same quiver, and these projective objects get mapped to the projective objects I mentioned before here. So these projective objects I got by doing this weird quantization and characteristic P trick turn out to be the objects which are mirror to these branes with holomorphic Lagrangians that are transverse to pieces of my skeleton. So that's where this equivalence came from. You should think of this somehow as being like, you know, if we knew how to define a Fukaya category of this horribly singular space Y01, then it should be the same as the category of coherent sheaves on that singular space. And then kind of what I did here was like, when I moved my parameter beta to what it was, somehow I was telling you not to resolve this space, but rather to kind of resolve it in some sort of, I don't know what words to say, inside the category of coherent sheaves somehow. And that's why I had to do all of this tricks with the P stuff to get this hyperplane picture to appear. So I could maybe just say a few words now about some generalizations. So one example, which I've spoken about before, which is work in progress, is the Springer resolution, T star G mod B. So now, so in this case, what are the hyperplanes that are going to appear? The hyperplanes, yeah. Maybe I should say the analog of the affine space in this case. The analog of my Y0 beta is going to be, I take an orbit inside a regular semisimple Lie group. This is an orbit in regular semisimple conjugacy class. Inside of, let me just say GLN or SLN. I'll do G equals SLN. And then I want to intersect it with the product of opposite Borels, which is the space. So this is just a conjugacy class of matrices. So it's a bunch of matrices where I've specified all the eigenvalues. And now this is going to be where the upper left minors are non-zero. So if my matrix looks like, you know, I require that this entry is non-zero and that AD minus BC is non-zero. So this has a map called the Gelfand-Cetlin map, which maps to the eigenvalues of the upper left minors. So this maps to C star times C star squared times dot dot dot, which is the eigenvalues of upper left minors. And then again, there's a hyperplane arrangement in here called the Gelfand-Cetlin hyperplane arrangement, which maybe I don't have time to write down, but this is a multiplicative version of the Gelfand-Cetlin arrangement, so you do it kind of periodically. And then the point is, once again, you get a bunch of chambers, and those chambers are going to correspond to components of your skeleton. Maybe I'll just write this here. Chambers in this periodic Gelfand-Cetlin arrangement correspond to components of an affine Springer fiber, which is the analog of this union of toric varieties we saw in this case. So the difference in the Springer resolution is that now these are not smooth varieties. Some of these can be horribly singular. So somehow like applying the same trick is going to get you some kind of generators, but you'll have a real hard trouble finding out some relations for your category. So there's some other ways to approach this, which I don't have time to talk about, but my point was just to convince you that somehow this thing with the hyperplanes appearing, and appearing also in the coherent sheaf side. Oh yeah, and I should mention that Ben Webster has a way of doing exactly an analogy to this and producing coherent sheaves corresponding to the different components, the different chambers in this arrangement. Just like we produce coherent sheaves here corresponding to the different chambers in this arrangement. So this is going to be quite a general story that should include this multiplicative Springer resolution and also multiplicative quiver varieties. And I think that's all I have time for today. So thanks.
Questions, comments?
Is there a relationship to something physicists call 3D identical mirror symmetry?
Yeah, that's a good question. As far as I can tell, I don't understand any relation to 3D mirror symmetry. So the 3D mirror to one of these hypertoric varieties is the Gale dual hypertoric variety. So the 3D mirror, the so-called 3D mirror to T star Pn is T star of, is a resolution of AN singularity. So that seems to be sort of a different direction. I've spoken to some people about this. Tudor de Moftet tells me he thinks it's interesting to sort of compose both kinds of mirror symmetry, and that should be some sort of duality. But no, as far as I can tell, this doesn't have a direct relation to the 3D mirror symmetry.